Hello friends, hope all of you are doing good. So let's continue our lecture 8 and we will start from the point exactly where we left in our last lecture. So we have been solving a partial differential equation corresponding to the one-dimensional wave equation. And we have seen the amplitude function which is the solution has two parts. One is the displacement part and another is the time dependent part. So we have already solved the displacement function x, okay, and now what is left to solve? The time dependent part. So the time dependent part can be directly solved from this equation. So this was the part of the equation that we got in last lecture by the process called separation of variables. So this is the form, and we have already recognized that k is negative of beta square, where we already found beta is equal to n pi over L. So we see that this equation is already existing in the form of this. So if we can recognize this one, so equation corresponding to the simple harmonic motion plus omega square x. Actually these are all function of t, x is a function of t is equal to 0. Okay, so now or we can write that this function minus, if we put the value of k as negative beta square, so this become v beta whole square t is equal to 0. So what we get here, that this equation actually corresponds to this equation. Okay, so this represents again a simple harmonic oscillation. So we can correlate that here omega square and v beta square performs the same function. So that means omega is nothing but v beta. Alright, so what is omega here? So definitely omega can be represented as velocity multiplied by beta, n pi over L. Alright, since omega contains a part n, so the value of omega is dependent on n. So in other words, we can write omega n is equal to this v n pi over L. Okay, so we can directly write this part as d to t dt dt2 plus omega n square t is equal to 0. Now we see you get back exactly this form. So here from our previous knowledge that how to solve a differential equation like this, we can directly write the solution dt is equal to, we can directly write that d cos omega n t plus e sine omega n t. Alright, so hopefully you can now recognize this equation that you have already seen it before. So of course this constant e contains the imaginary part. So this is now our t. So we have already got our x and now this is our answer for t. So finally we have to express uxt as the product of the two fragments, product of the two fragments solution that we got. So let's quickly rewrite it over here. Okay. Now that we got both the x part and the t part, we can take the product of the two to get the final solution. So the final solution looks like this is equal to b sine this part multiplied by the time dependent part. So overall what we can do further, that we can take the b and multiply with d to simplify the constants of integrations. So if we multiply that, then let's introduce a new constant f over here and g over here. So g means multiplication of b times e. And then everything all together multiplied by sine n by x by L. So if we take a look at this particular solution, you see that this value of u is actually dependent on the value of n. So where we already know that n is equal to 1, 2, 3, etc. It can go up to infinity, but of course excluding 0. So therefore, whatever the value you take for n is equal to 1, 2, 3, u, that means the amplitude function, is going to be defined by this. And also, similarly, f and g values, since those things came from applying the particular boundary conditions, uh, because it also already contains the part b. So f and g would also change with respect to n. So to express uxt, we should use that superscript n. So un is equal to fn cos this part plus gn sine this part. So we can tell overall that this is the final solution for the vibration of one-dimensional wave equation, or vibration of a string attached in both ends. But this is not the all, so we can further generalize it. So we can write a more general solution. The more general solution is what? So now for each value of n, whatever the un value we get, that can serve as a solution to the partial differential equation, or the vibration of one-dimensional string problem. But mathematically it can be shown that the summation of any of these individual modes means, if we take the summation of u1 and u2 and u3, and then the resultant summation, it can be shown that it is also a solution to the same partial differential equation, or the solution to the one-dimensional wave equation. So therefore, we can write the general solution just like this here. So the general solution can now be written as u xt is equal to summation of this whole part, means once again I write the summation is from n is equal to 1 to infinity. So now you see that we just have added a simple summation part, right? And this becomes our final general solution. So this means not only the individual un, but also their summation can form an acceptable solution for this problem. Okay. So now, since that we have understood the solution, the next question lies that what are the physical interpretation of the solutions that we just got. Okay. So before we go any further, I want to ask you a question. That is, here we have the omega part. So we have learned about omega or omega n. Now, in our previous lecture, in one of our previous lectures, we have seen that omega can be represented as the 2 pi times of nu. So here if it is n, so omega n, then we have to call it nu n. So my question is, can you find out the value of nu n? So that means I want you to figure out the values of nu1, nu2 and nu3, etc. The first 3 modes. Okay, so by taking n is equal to 1, 2, 3, 1, 2, 3, etc. So it is up to you to do. Alright, so now let's come back to our physical interpretation. So here is the physical interpretation, that when n is equal to 1, corresponding to that we get a frequency nu n or nu1. So when the string is vibrating with nu n is equal to 1, then the corresponding frequency is called the first harmonic or fundamental. So for n is equal to 2, it is called the second harmonic or the first overtone, and for n is equal to 3, it is called the third harmonic or the second overtone. So now let's try to see the physical picture of in what mode the string vibrates for the corresponding n. So each of those vibrations are called the mode. So this one is called the fundamental mode, or this one is called the first overtone mode, and also this one is called the second overtone mode. So these are the different modes. So for the fundamental mode, the string starts to vibrate this way. So both end attached. So the string actually vibrates symmetrically. So here x is equal to 0 and here x is equal to L. Alright. And there is no node in between. Now what happens here at the first overtone mode, the string undergoes a node here. Okay. So node means a point where the displacement is 0, that is u xt is 0 all the time. And so here x is equal to L, sorry. And for the third harmonic, so this becomes the picture. So there will be two nodes, alright? So the string will vibrate this way. So this is the other position. Okay. So here we have a node, and here we have two nodes. So this is one node and this is another node. Alright. So the question is, for the fundamental there is no node, for the first overtone one node, and for the second overtone there are two nodes. So how many nodes are appearing? So you see the number of nodes is equal to n minus 1, where n is the mode, the number of mode. Okay. So here, for example, n is equal to 1, so no node 0. Here n is equal to 2, so node is equal to 1, and so on. Okay. So now definitely you can verify this. So you can take the first solution, use n is equal to 1. So u1 xt, you see for all values of x, u never becomes 0. And here you can prove, so it's your job to do, prove that for x is equal to L by 2, alright, mu 2 becomes 0. Okay. And also you find out the positions here at what value mu 3 becomes 0. Alright. So this is the way we can visualize the vibration of strings. And another thing that we want to draw your attention, that this kind of vibration generates a wave, you see. So this represents a wave. What kind of wave is this? Of course, you know the answer. So these would generate a stationary wave. And I have told you earlier also that we are studying the vibration in one-dimensional string because this is the classical picture of a stationary wave. And we know in quantum mechanical picture, electron is nothing but a standing wave or a stationary wave. So how can we understand that these waves are stationary, or how to differentiate, recognize that whether a wave is stationary or propagative? So here is the answer, that with respect to x and t, okay, the position of the node becomes stationary. So the node never changes. So as well as the maxima. So here I have the maxima, the position. Okay, so this is called the position of maxima. This doesn't change. So once again I repeat myself. We only call a wave a stationary wave when we see with respect to position or time, both the position of node and the maxima does not change, appears stationary. So then only we will call that wave a stationary wave. All right. So before we finish today's lecture, I want to pose a couple of questions for you, and it is for you to think and then you try to find a solution. Of course, you can take the help from your textbook. Okay. So here I am framing the question for you. So here I would like to draw your attention on few facts. That is, number one, mathematically it can be proven that a standing wave is a superposition of traveling waves in opposite direction. Okay? So the thing is, you have to prove this. Means this one. Of course, you can take the help of your textbook and you can show that when two traveling waves propagate from opposite direction, it gives rise to a standing wave. And similarly, the reverse is also true. Also, you do not have to show this mathematically, but you just appreciate the fact that a superposition of standing wave, a superposition of what? A superposition of different normal modes containing the standing wave gives rise to a traveling wave as well. Okay, so you see the properties of a traveling wave is somewhat hidden within the standing wave. And of course, the last point is that any complicated general wave motion, okay, like our vibration of one-dimensional string, it can be represented as a sum and superposition of different normal modes, and it becomes a fundamental property of oscillation. Okay, and the last point is the general solution to that kind of wave equation. What kind of wave equations? A wave equation that represents that the sum or superposition of normal modes can give to another solution. Okay, so the general solution to the wave equation becomes linear in nature, and that kind of equation can be expressed in terms of a Fourier series. All right. So these kind of oscillatory functions that can be represented in Fourier series becomes a key part in understanding the mathematical aspects of vibrational spectroscopy. So we will follow that in some other topic, in some other courses. So these three are the most striking features of the vibration of one-dimensional wave equation, or the vibration of a string. Okay, so now before we finish, we would like to tell you something, that whatever we have seen so far as a solution to the vibrating one-dimensional string, or the one-dimensional wave equation, so the solution of the vibration of a string is represented in terms of this. Okay, you must agree, that is the amplitude function dependent on n and is a function of x and t. So what if we have to deal with un only function of x, not with the function of t? So that means our life would have been so simple if we have to do that. All right. Now let me tell you a fact, that whenever we will deal with the wave function of electron, that is psi n, similarly, okay. So this is the amplitude function, also the psi n, it also represents an amplitude function, amplitude of the wave that represents electron. That means the amplitude of that standing wave representing electron. So this psi n is also the function of x and t. All right, but we chemists, okay, means the quantum chemistry, in quantum chemistry, we fortunately, in major cases, we only have to deal with the function of x, that means psi as a function of x. So you see, for us, that means for the learners of quantum chemistry, life is much simpler than the students of quantum physics. Unfortunately, they had to deal with from the dependence of psi with respect to both x and t. So here, most of the cases, we will follow the time independent situation. So other words, so here we will be learning a little bit simpler stuffs. I hope you enjoyed it. So in next lecture, lecture 9, we will follow the case of the vibration in a two-dimensional membrane. Okay, so till then, goodbye. See you in the next lecture.